Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the blue square? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Inside the blue square ABCD sits a red triangle EFG whose area is given as 30. We want the area of the whole square. Our chain will run from two short corner lengths all the way out to the side of the square. Point F rides the right edge segment AB at distance 3 from corner A, and point E rides the top edge segment AD at distance 4 from A. The third vertex G lands on the left edge segment DC. These three placements lock the red triangle into the square. In the top right corner, a small right triangle AEF is formed. Its vertical leg segment AF is 3, and its horizontal leg segment AE is 4, meeting squarely at corner A. These two lengths start the whole chain. Because the angle at A is a right angle, the hypotenuse segment EF obeys the Pythagorean theorem. So segment EF squared equals 3 squared plus 4 squared. Let us evaluate the right side next. 3 squared is 9, and 4 squared is 16. Adding them gives 25, so segment EF squared is 25. A single square root now finishes this leg. Taking the square root of 25 gives 5, so segment EF equals 5. This is the classic 3, 4, 5 right triangle, and segment EF will serve as one leg of the red triangle. The red triangle EFG has its right angle at E, so segment EF and segment EG are perpendicular legs. We already know one leg, segment EF, is 5. The given area will pin down the other leg, segment EG. For a right triangle, the area is 1/2 times the two legs. So 1/2 times segment EF times segment EG equals the given 30. This is the equation that will unlock segment EG. Substituting segment EF equal to 5 into the area equation gives 1/2 times 5 times segment EG equals 30. Now only segment EG is unknown, so we can isolate it. Multiplying both sides by 2 clears the 1/2 and gives 5 times segment EG equals 60. One more division will free segment EG by itself. Dividing both sides by 5 gives segment EG equal to 60 over 5, which is 12. So the second leg of the red triangle is 12. The red triangle is right-angled at E with legs 5 and 12, so its hypotenuse segment FG satisfies segment FG squared equals 5 squared plus 12 squared. We compute the right side next, mostly as a sanity check on the shape. 5 squared is 25 and 12 squared is 144. Their sum is 169, so segment FG squared is 169. The square root of 169 is 13, so segment FG equals 13. A 5, 12, 13 triangle sits tilted inside the square, which confirms our legs are right. To measure how far segment EG reaches, box it in. Mark H straight down from E, then draw the vertical leg segment EH and run the horizontal leg left to G. Triangle EHG is right-angled at H, with hypotenuse segment EG equal to 12. Our first insight is this: the two right triangles are similar. The two hypotenuses are segment EG equal to 12 for the box and segment EF equal to 5 for the corner triangle. So the scale factor is segment EG over segment EF, that is 12 over 5. Every corner leg gets multiplied by this ratio. Under the rotation, the corner leg of 3 corresponds to the horizontal leg segment HG. Multiplying 3 by 12 fifths gives 36 fifths. That is 7.2. This horizontal reach is the piece we need for the side. The corner leg of 4 corresponds to the vertical leg segment EH. Multiplying 4 by 12 fifths gives 48 fifths. That is 9.6. We will use this later to check that G stays inside the square. A second insight now finishes the structure. The square side is a sum of horizontal reaches. Putting in the numbers, the side equals 4 plus 36 fifths. To finish the addition, we need a common denominator. Writing 4 as 20 fifths lets both terms share the denominator 5. So the side is 20 fifths plus 36 fifths. Adding the numerators, 20 plus 36 is 56, so the side is 56 fifths, or 11.2. The square side is now known exactly. As a check, the vertical reach segment DG equals the box leg segment EH, which is 9.6, comfortably less than the side 11.2. So G really does land on edge segment DC, and the red triangle fits inside the square just as drawn. The area of a square is the side squared, so the area equals 56 fifths squared. We square the numerator and the denominator separately. 56 squared is 3,136, and 5 squared is 25, giving 3,136 over 25. As a decimal, 11.2 squared is 125.44, which agrees. So the answer is 3,136 over 25. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.